Imagine trying to predict how a molecule will behave under certain conditions. Sounds simple. In fact, this is one of the most difficult tasks in modern science. Every electron in the molecule interacts with every other electron, and the number of possible states grows exponentially with each new atom. A classical computer, even the most powerful supercomputer in the world, is simply not able to accurately calculate the behavior of a molecule of average complexity. And that's where quantum simulations come in, a revolutionary approach that uses quantum nature itself to simulate quantum systems. The story of this idea dates back to the 1980s, when physicist Richard Feynman asked a simple but ingenious question. Why not use a quantum system to simulate another quantum system? It was like an epiphany. We tried to simulate the quantum world with the help of classical computers that work on a fundamentally different logic. It's like trying to draw a three-dimensional object on a flat surface. You can get closer, but something is always lost. The problem of modeling molecules on classical computers is related to the fact that quantum systems exist in a superposition. They can be in many states at the same time. When we try to describe even a simple water molecule mathematically, we have to take into account all the possible positions of all the electrons, all their spins, all the possible interactions. The number of variables becomes astronomical. For a molecule of 50 atoms, it would take more memory than there are atoms in the universe to fully describe its quantum state in a classical way. Scientists have been using approximations and simplifications for a long time. They developed a lot of clever methods to get around this problem: density functional theory, Monte Carlo methods, various approximate circuits. These techniques work surprisingly well for many tasks, but they have fundamental limitations. There are entire classes of molecules and materials that we simply cannot accurately model using classical approaches. This is especially true for systems with strongly correlated electrons. Materials where electrons interact so intensely that they cannot be considered independently. Quantum simulations work in a completely different way. Instead of calculating all possible states, a quantum simulator physically reproduces the behavior of the system being studied. It's like the difference between calculating the trajectory of the ball and actually throwing it. You can calculate as much as you want on paper, but sometimes it's easier to just throw the ball and see where it goes. There are two main approaches to quantum simulations. The first is analog quantum simulators. They use one quantum system to directly simulate another. Imagine that you want to understand how electrons behave in a new material. You create a system of ultra-cold atoms. Tune their interactions so that they mathematically correspond to the interactions of electrons in your material, and observe what happens. Atoms become analogous to electrons, and their behavior reflects the behavior of a real system. Experiments with ultra-cold atoms and optical lattices are one of the most advanced platforms for analog quantum simulations. Scientists cool atoms to almost absolute zero. We're talking about temperatures in millionths of a degree above absolute zero. At such temperatures, quantum effects dominate. Then, the laser beams, intersecting in a certain way, create a periodic structure, an optical lattice similar to the crystal structure of a solid. Atoms fall into this lattice like eggs fall into a tray. By manipulating the intensity and configuration of the lasers, researchers can precisely control how strongly atoms interact with each other and how easily they can move between lattice nodes. This makes it possible to reproduce various models of quantum systems. For example, you can model the Hubbard model, one of the fundamental models in condensed matter physics, which describes how electrons move through a crystal lattice and interact with each other. Hubbard's model sounds simple, but its exact solution for large systems remains one of the great unsolved problems of physics. It is believed that understanding this model could explain high-temperature superconductivity, a phenomenon that we observe experimentally but still do not fully understand theoretically. With quantum simulations, scientists can literally create a physical implementation of Hubbard's model and study its behavior directly. Another interesting example is the use of ion traps for quantum simulations. Ions are charged atoms that can be held and manipulated using electromagnetic fields with incredible precision. Ions line up or in more complex configurations, suspended in a vacuum, isolated from the environment. Laser pulses allow you to precisely control the quantum state of each ion and create interactions between them. The advantage of ion traps is that they provide very high inspection accuracy. Each ion can be addressed individually, and its state can be accurately measured. This makes ion trap systems particularly suitable for simulating quantum chemistry, where accuracy is critical. Scientists have already used ion traps to simulate simple molecules, such as a hydrogen molecule, and are gradually moving on to more complex systems. The second approach is digital quantum simulators, which are essentially quantum computers programmed to solve a specific simulation problem. It uses quantum bits, or qubits, which are quantum analogs of classical bits. But unlike a classical bit, which can be either 0 or 1, a qubit can be in a superposition of both states at the same time. Digital quantum simulators are more flexible than analog ones. You can reprogram them to simulate different systems by applying different sequences of quantum operations called quantum gates. This is similar to the difference between an analog and a digital computer. A digital computer is more versatile, although a specialized analog device may work more efficiently for a specific task. One of the most exciting applications of quantum simulations is to simulate chemical reactions. A chemical reaction is a quantum mechanical process. When two molecules collide and react, their electrons are redistributed, new chemical bonds are formed, and old ones are broken. All of this happens at the quantum level, driven by wave functions and quantum interference. Pharmaceutical companies spend billions to develop new drugs, and a big part of that process is predicting how a candidate molecule will interact with proteins in the body. Now, this process is largely based on experiments and approximate calculations. Imagine if we could accurately predict how any molecule would interact with any protein, even before the molecule is synthesized in the lab. This would revolutionize drug development, reducing time and costs by orders of magnitude. Quantum simulations also open up possibilities in the field of catalysis. Catalysts are substances that accelerate chemical reactions without being consumed. They are absolutely critical for modern industry. Fertilizer production, exhaust gas purification, plastics production, all this depends on catalysts. But the development of new catalysts is still largely an art based on intuition and trial and error. The problem is that catalytic processes occur on the surface of the material, where individual atoms interact with the reactant molecules in the most complex way. These interactions are deeply quantum mechanical. Quantum simulations can allow us to understand these processes at a fundamental level and purposefully design catalysts with the desired properties. A particularly interesting application is the modeling of the nitrogen fixation process. Nitrogen from the air needs to be converted into ammonia to make fertilizer, but the nitrogen bond is incredibly strong, and breaking it requires a huge amount of energy. The Haber-Bosch industrial process, used for more than a century, operates at high temperatures and pressures and consumes about 2% of the world's energy. Meanwhile, some bacteria do this at room temperature with the help of the enzyme nitrogenase. If we could understand how this enzyme works at the quantum level and reproduce its mechanism artificially, it would have huge implications for sustainable agriculture and energy. Quantum simulations also play a key role in the development of new materials. Modern electronics is based on materials with very specific properties, semiconductors with a certain band gap, materials with high mobility of charge carriers, insulators with a certain dielectric constant. All of these properties are ultimately determined by the quantum mechanics of the electrons in the material. There are entire classes of materials with exotic properties that we still don't fully understand. High-temperature superconductors, which conduct electricity without resistance at temperatures much higher than conventional superconductors, remain a mystery. We know they work, we can produce them, but we can't predict exactly which materials will be superconductors and why. Quantum simulations can help solve this mystery. Topological materials are another exciting field. These materials have special surface states protected by the topology of their electronic structure. Electrons on the surface of a topological insulator can move without scattering, making them potentially useful for the electronics of the future. But predicting which materials will have topological properties requires the precise modeling of their electronic structure, an ideal problem for quantum simulations. One of the most ambitious goals is to simulate photosynthesis. Plants convert sunlight into chemical energy with astounding efficiency using quantum effects. When a photon of light hits a chlorophyll molecule, it creates an exciton, a bonded pair of an electron and a hole, which must then travel to the reaction center, where the chemical transformation takes place. Studies show that this energy transfer uses quantum coherence. The exciton explores all possible paths simultaneously and chooses the most efficient one. Understanding these quantum effects in photosynthesis could lead to the creation of artificial photosynthetic systems much more efficient than solar panels. Imagine materials that could directly convert sunlight into chemical fuels with an efficiency close to the theoretical limit. This would solve humanity's energy problem. Quantum simulations are also important for understanding quantum phase transitions. In classical physics, we are familiar with phase transitions. Water turns into ice or steam when the temperature changes. But there are also quantum phase transitions, which occur at absolute zero temperature, when a system changes from one quantum state to another due to a change in some parameter, such as a magnetic field or pressure. These quantum phase transitions are associated with exotic states of matter. For example, quantum spin fluids are a state where the magnetic moments of atoms remain disordered even at absolute zero due to quantum fluctuations. These states are potentially useful for quantum computing, but they are very difficult to study experimentally. Quantum simulations provide a control platform for investigating these phenomena. An important aspect of quantum simulations is the ability to study non-equilibrium processes. Most of our theoretical tools work well for systems in equilibrium, but the real world is full of non-equilibrium processes, chemical reactions, biological processes, the operation of motors and batteries. Quantum simulations allow us to observe how a quantum system evolves over time, how it relaxes to equilibrium, or how it behaves under continuous influence. One of the most interesting recent areas is the use of quantum simulators to study thermalization in quantum systems. When a classical isolated system is thrown out of balance, it eventually relaxes to thermal equilibrium, something we intuitively expect. But in quantum mechanics, the situation is more complicated. Some quantum systems can exhibit a phenomenon called mini-particle localization, where they're never thermalized due to disorder and quantum interference. This is not just an academic interest. Understanding how quantum systems retain or lose information is critical to quantum computing. A quantum computer is essentially an isolated quantum system that we try to keep out of equilibrium long enough to do the calculation. Studying the dynamics of quantum systems through simulations helps us understand how to better design and protect quantum computers from decoherence. Decoherence is the main enemy of quantum technologies. It is a process in which a quantum system loses its quantum properties due to interaction with its environment. The quantum superposition is destroyed, entanglement disappears, and the system becomes classical. For quantum computing and quantum simulations, decoherence limits the time we can maintain a quantum state. Interestingly, quantum simulations themselves can help understand decoherence. By creating controllable quantum systems and observing how they interact with different types of environments, we can study the mechanisms of decoherence and develop strategies to suppress it. This creates a positive feedback loop. Quantum simulations help improve quantum technologies, which in turn make more powerful quantum simulations possible. There are also exciting prospects for using quantum simulations to simulate quantum gravity and cosmological phenomena. It sounds fantastic, but the idea is that some aspects of quantum gravity can be related to the behavior of quantum condensed matter systems through a mathematical analogy called duality. By building certain quantum systems in the lab, we could study phenomena similar to those that occur in black holes or the early universe. For example, there are suggestions that analogs of black hole event horizons can be created in systems of ultra-cold atoms. Hawking radiation, the theoretical radiation from black holes, has never been observed in an astrophysical context because it is incredibly weak. But its analog could be found in a quantum simulator, which would confirm one of the most fundamental predictions of the quantum theory of gravity. The practical implementation of quantum simulations faces many technical challenges. It is necessary to create and maintain high-quality quantum states, accurately control interactions, and effectively measure results. Each platform, ultra-cold atoms, ion traps, superconducting qubits, photonic systems, has its advantages and limitations. Ultra-cold atoms provide very pure systems with well-controlled interactions, but they are difficult to scale to very large sizes. Ion traps provide high accuracy, but the number of ions that can be contained in a single trap is limited. Superconducting qubits are easier to scale, but they are more susceptible to noise and decoherence. Photonic systems operate at room temperature, but it is difficult to create strong interactions between photons. Researchers are working on hybrid approaches that combine the advantages of different platforms. For example, ions can be used to store quantum information with high precision, and photons can be used to quickly transfer information between distant ions. Or combine superconducting qubits with mechanical resonators to create new types of interactions. An important issue is the verification of the results of quantum simulations. How can we be sure that the quantum simulator actually correctly simulates the system being studied? For small systems, we can compare the results with classical calculations or with experimental data. But the whole point of quantum simulations is to study systems that are classically unsolvable. For such systems, we can't just test the answer. Scientists are developing methods for self-control of quantum simulations. One approach is to verify that the simulator correctly reproduces known physical laws, such as the conservation of energy or the symmetries of the system. Another approach is to use several independent quantum simulators and compare their results. If different simulators built on different principles produce consistent results, it increases our confidence. There's also an interesting connection between quantum simulations and machine learning. Machine learning methods are used to analyze data from quantum simulators, to optimize simulation parameters, and to predict the properties of quantum systems. On the other hand, quantum simulations are used to understand how neural networks work, which are themselves complex multi-particle systems. Recently, researchers have begun experimenting with quantum machine learning, where quantum computers or simulators are used to train machine learning models. It is hoped that quantum effects such as superposition and entanglement can provide an advantage for certain machine learning tasks. Although the field is still in its infancy, it demonstrates how quantum technologies are beginning to intertwine with other cutting-edge areas of computer science. One promising application is the use of quantum simulations for optimization. Many problems in industry, logistics, and finance come down to the search for a minimum of a complex function of many variables. Classical optimization algorithms often get stuck in local lows. Quantum systems, thanks to tunneling and quantum fluctuations, can explore the decision space more efficiently. Quantum annealing is a technique that uses a quantum system to find the ground state that corresponds to the optimal solution. D-Wave has been producing quantum annealers for many years. Although the question of whether they truly provide quantum acceleration for practical tasks remains the subject of intense research and debate. However, it demonstrates how quantum simulation ideas are starting to make their way out of the lab and into commercial applications. It is important to understand that quantum simulations will not replace classical calculations and experiments, but will complement them. For many tasks, classical methods remain the most effective. Experiments are necessary to test theories and detect unexpected phenomena. Quantum simulations occupy an intermediate niche. They allow you to study systems that are too complex for classical simulations, but at the same time more controllable and tunable than real experiments. The future of quantum simulations looks incredibly promising. As technology advances, we will be able to simulate larger and more complex systems. Quantum simulators with hundreds or thousands of qubits are already becoming a reality. With such systems, we will be able to simulate biological molecules, complex materials, catalytic processes with unprecedented accuracy. Imagine a future where a chemist developing a new drug can enter the structure of a molecule into a quantum simulator and get an accurate prediction of all its properties. How it will bind to the target protein, what side effects it can cause, how it will be metabolized in the body. Or a materials engineer who could design a new material with specified properties, test it in a quantum simulation, and only then synthesize it in the laboratory, already being confident in the result. Such a future may be closer than we think. The last few years have shown incredible progress in quantum technologies. Companies and research groups around the world are investing billions in the development of quantum computers and simulators. We are on the cusp of a quantum revolution that could change science, technology, and industry as radically as the digital revolution did in the last century. Quantum simulations are not just another computational tool. It's a new way of understanding nature, a way of using the most fundamental laws of physics to solve practical problems. This is the embodiment of Feynman's idea that nature itself can be a computing device. And as we learn to better control quantum systems, we are opening up not just new technologies, but also new windows into the fabric of reality at the most fundamental level. This ending raises philosophical questions about the nature of simulation and reality. If we can use a quantum system to accurately simulate another quantum system, where is the boundary between simulation and reality? In a sense, a quantum simulator doesn't just compute the behavior of a molecule. It becomes that molecule, at least as far as its quantum properties are concerned. This idea links quantum simulations to broader questions about the nature of computing and physical reality. Some physicists have speculated that the universe itself may be a kind of quantum computation. Each interaction of particles is a computational step. The evolution of the wave function is the execution of an algorithm recorded in the laws of quantum mechanics. From this point of view, by creating quantum simulators, we create small universes that work on the same principles as our own. Of course, current quantum simulators are still very far from being able to create something similar to an entire universe or even a living cell. But the direction of development is clear. Every year, the systems are getting bigger, the control is becoming more accurate, and the possibilities are expanding. We are moving from simulations of the simplest molecules to complex materials, from model systems to real chemical processes. What's particularly exciting is that it's not just an academic exercise. Quantum simulations are already starting to have a real impact on industry. Chemical and pharmaceutical companies are investing in quantum technologies, understanding their potential to accelerate the development of new products. Materials manufacturers see opportunities to create next-generation batteries, more efficient solar panels, and new catalysts for green chemistry. The energy sector is particularly interested. If quantum simulations help us create more efficient catalysts to produce hydrogen from water, or materials for larger batteries, or artificial photosynthetic systems, it could be the key to solving the climate crisis. The transition to sustainable energy requires breakthroughs in materials science and chemistry, precisely those areas where quantum simulations promise the greatest impact. There are also challenges that need to be recognized. Quantum technologies are still very expensive and require high qualifications to work with them. Most quantum systems operate at temperatures close to absolute zero, which requires sophisticated cryogenic equipment. Scaling quantum systems remains a major technical challenge. And even when we have powerful quantum simulators, we will need new algorithms and methods to use their capabilities effectively. But the history of science and technology shows that such challenges can be overcome. The first computers took up entire rooms and required special operating conditions. And now we have devices millions of times more powerful in our pockets. The first lasers were lab curiosities, and now they're everywhere from turntables to medical devices. There is no reason to think that quantum technologies will not follow a similar path from laboratory prototypes to widespread use. Education and training of specialists are becoming critical. We need scientists and engineers who understand quantum mechanics, chemistry, materials science, and computer science. Interdisciplinarity is not just a buzzword, but a necessity for work in the field of quantum simulations. Universities around the world are launching new programs, companies are creating educational initiatives, and a new generation of quantum specialists is being formed. International cooperation also plays an important role. Quantum science is a global enterprise where research groups from different countries share ideas, methods, and results. Large quantum simulators are often built by international consortia. Openness and knowledge sharing accelerate progress and ensure that the benefits of quantum technology are widely available. Ethical and social aspects also deserve attention. As quantum simulations become more powerful, they can create new kinds of inequality between those who have access to these technologies and those who don't. It is important to think about how to make the benefits of quantum technologies available not only to rich countries and large corporations, but also to developing countries, small businesses, and academic researchers with limited resources. There are also questions about potential dual use. Technologies developed for quantum simulations can have applications not only for peaceful purposes. Accurate modeling of chemical reactions can help create new drugs, but theoretically new dangerous substances. As with any powerful technology, you need thoughtful policies and regulation to maximize benefits and minimize risks. Looking into the future decades ahead, you can imagine a world where quantum simulations have become a common tool for scientific research and industrial development, where every major chemical company has access to quantum simulators to design new molecules, where the development of new materials is accelerated by orders of magnitude due to the ability to accurately predict their properties before synthesis, where we understand biological processes at the quantum level and can purposefully modify them. This future could include quantum simulations to help solve problems that seem unsolvable today. Creation of room temperature superconductors that revolutionize power transmission and transportation. Developing effective catalysts to capture carbon dioxide from the atmosphere, helping to reverse climate change. Understanding the mechanisms of disease at the molecular level, leading to personalized medicine with unprecedented precision. But perhaps most importantly, quantum simulations are changing the way we think about nature. They remind us that we ourselves are part of the quantum universe, and that by using quantum principles, we can achieve things that are impossible in the classical world. They show that the boundary between the observer and the observed, between the instrument and the object of study, may be more blurred than we thought. Quantum simulations are a bridge between basic science and practical applications, between abstract quantum mechanics and concrete technologies that improve our lives. They embody the idea that understanding the fundamental laws of nature is not just an intellectual satisfaction, but also a way to solve the real problems of humanity. As we stand on the cusp of the quantum age, we are at a unique point in history. The tools we build today will determine tomorrow's opportunities. Quantum simulations are not just a new technology, they are a new paradigm of scientific research, a new way of interacting with the world at its most fundamental level. And like all the great scientific revolutions of the past, this revolution promises not only new knowledge and possibilities, but also a new understanding of our place in the universe. The journey is just beginning. Every new quantum simulator, every successful simulation of a complex molecule, every discovery of a new material using quantum methods is a step into a future that seemed like science fiction just a few decades ago. But this future is becoming a reality right now, in laboratories and industrial facilities around the world. And the most exciting thing is that we can't even fully predict where this path will take us. This is what makes quantum simulations so exciting. They open doors to the unknown, offering tools to explore what was previously unattainable. In this sense, they truly embody the spirit of scientific inquiry, to use what we know to discover what we do not yet know.